Thanks very much, Dr. Lynch and Vice President Bozega Osborne. One innovative aspect of this where suddenly I'm supposed to moderate my parents' lecture series. It's really, I think there's another truth. I don't think Einstein ever stated this, but a child is always nervous being watched by his parents. So I'm going to do what I can here. So talking about innovation, entrepreneurship, I'm going to be a little bit family-oriented here, but you know, today we think about somebody, some 20-something starting off a social networking thing that you never quite understand why this makes sense. And what I think of is my own background. My grandfather, Oliver Cheriton, was an entrepreneur with innovation because he homesteaded in Saskatchewan. And you know, when you're out there homesteading, you have to solve real problems, and there's not a corner store to go to buy everything you need, and a lot of farm equipment was still evolving pretty rapidly, and so there's a lot of innovation that's required, and really required because there's nobody else around to help you with it. And of course, a farm is a company in itself. You're your own boss, and you have to make a living at it. And I think that aspect of confronting problems and coming up with solutions to them, and I think, I like to think there's a Cheriton tradition, which is to not come up with just a good enough solution, but try and come up with a really good solution, because it's more satisfying and it does produce a better result. And I feel privileged that I think my dad carried that tradition through at the next level, and as an electrical engineer and through to forensics, and I tried to escape out of that tradition by becoming a musician, but it didn't work out too well, and somehow I gravitated back to being involved in technology and really engineering as well, and the same sort of problem solving that I think my grandfather did and my father did, and the same excitement of finding a really good solution to something rather than just a conventional solution or a good enough solution. So I think that there's a lot of innovation, there's a lot of entrepreneurship that are around us that we can draw on, that's not purely somebody starting a funny startup, but people that are taking that kind of command of their life. And I think we should look at the pioneers of this country as people that were both entrepreneurs and innovators. And whenever you encounter somebody who says, oh, I couldn't risk doing a startup, think about the people that took the risk to coming to this country in the early 20th century, and it was colder then, and you know, making their living on a farm when there was nobody that was backing them up. I think it has to be an inspiration to us all. So today, rather than listening to me too much, I think what's going to happen in the future is dependent upon young people like we have gathered here. And so let me introduce Jocelyn Bachman, who's at my far right, and Nir Kaczynski, who's in the middle, and Catherine Evans. And I was supposed to introduce them, but there's this long introduction of them in the program, and I thought, I can't do justice here, so I refer you there. They have tremendous background. They've all been doing some fairly interesting research. And they're all going to spend 2 minutes just introducing themselves and their area, and then each will have an opportunity of 10 minutes each, and then there'll be an exam for the audience at the end, so pay attention very carefully. So, without further ado, let's start off with Jocelyn. And your 2 minutes are starting. Make it good.
Good. Okay. So my name's Jocelyn, and I'm currently in my second year of my PhD. I'm actually studying my PhD in physics, but don't worry. I graduated from my master's in electrical engineering and my bachelor's in engineering physics from the U of A here, so I'm an engineer. And tonight, I'll be telling you a little bit about nano-optomechanical sensors, which sounds terrifying when I phrase it like that. but it's basically nano, small things, opto, light, mechanics, which is moving parts around us, and sensors. So hopefully that little bit of a teaser gets you guys excited for my 10-minute presentation, and I'll pass it off to Nir.
Good evening, everyone. First of all, thank you for the opportunity of being here. So I'm a PhD student in my third year in the electrical engineering department. I also did my undergrad here at the U of A in electrical biomedical engineering. I'll be talking a little bit about femtosecond laser manipulation of cells and neurons. This is a mouthful, but as you see in my presentation, it's talking about the use of extremely short laser pulses in order to do something more useful with cells and neurons, such as cell surgery and attachment of cells or neurons to each other. Catherine?
So my name is Catherine Evans. Is this? I think it's on. Oh, there we go. Okay. So my name is Catherine Evans. I'm here from the Department of Mechanical Engineering, and I did my undergrad in mechanical engineering here as well with the biomedical option. Right now I'm working with two different co-supervisors. So Dr. Jason Carey from the Department of Mechanical Engineering, and he's the coordinator of the biomed program, and Dr. Jacqueline Hebert in the Faculty of Medicine, who also works at the Glenrose, advising on amputees. And I'm going to talk to you a little bit about some of the work that we're doing to help provide sensory feedback or a sensation of touch to amputees using robotic prosthetic arms.
So this clearly promises to be an interesting but challenging evening to keep up with this. I was trying to practice some of these words before I came here, so hopefully I can say some of them as well as they can. So without further ado, shall we turn it over to Jocelyn to have your 10 minutes to present this? And,
Alrighty, so as I mentioned in my introduction, I'm going to be telling you a little bit about nanomechanical sensors. But since we don't necessarily know exactly what nano is right off the bat, I'll start by telling you a little bit about what nanotechnology is. So typically, we define nanotechnology as devices or materials that have feature sizes of around 100 nanometers. To put this in perspective for you a little bit, a single human hair, which we can see, it's pretty small, but it is visible to our eye, is actually much, much larger than nanotechnology features that I work with. So you can see here, oh, I have two screens. This is a nanotechnology feature here. This is an image of a human hair, and this is 50 micrometers large compared to 500 nanometers. So that's quite a big difference. So working with things that are very, very small. I'll throw some numbers at you too to hopefully put some of this in perspective. So a micrometer, which is what this symbol means here, is 10,000 times smaller than a centimeter. And a nanometer is 10 million times smaller than a centimeter. So these are very, very small scales that I work with. So in order to see this nanotechnology, because I can't see it with my bare eyes, and I can't really see it with a regular light microscope either, I have to use something called scanning electron microscopy, or SEM. And SEM is very similar to a regular microscope and how it works, but we actually use a beam of electrons to look at the samples instead of light. And so what I've shown here are two SEM images, and you'll see these types of images throughout the rest of my presentation. And these are images that I did during my master's. And this is a very large device relatively here. And when we can see some small features, but when we zoom in, we can really see the small details down at the nanoscale. And so this is a very powerful tool for us to look at some of our devices. And so now I'll tell you a little bit about nanomechanical systems. So nanomechanical systems are, of course, very small, but they're also free to move, which is the really interesting part. So you can see here, this is a nanomechanical device. It is not attached at the base layer underneath, so there's freedom of movement. And so that device can then move in lots of different directions, and there's very complex types of nanomechanical systems. The two that I work with typically are a little bit simpler. So this is a bridge structure here, and this is a cantilever structure. And this one will move in this direction. This one actually moves in this direction. So we can do all kinds of things with this. There's also a wide range of dimensions that I work with. So these are about 200 nanometers tall, range from 500 nanometers wide down to only 150, and they can be quite long. So the larger one on the bottom is 20 micrometers long. The smaller cantilever on top, only 3 microns long. So there's quite a lot of flexibility with this technology. And now how they work is actually very similar to a guitar string. So when you strum a guitar, the string vibrates and you hear a sound. And that sound is the sound of the string oscillating or vibrating at about 100 vibrations per second, or 100 hertz. My devices have the same operating principle. They vibrate at about 1 million vibrations per second. So it's just a little bit faster than a guitar string. With that, we can kind of keep in mind that these are very small, very fast devices. And so how do we even see these vibrations? How can we detect them? They're so fast. And we do that using light. And so light is very sensitive to these vibrations, so it's a really nice tool for us to use. We can also direct light very easily on the scale of our samples by using something called a waveguide. A waveguide is basically a wire for light. So instead of carrying electricity, it carries light. And so that's what you can see here. This is our input waveguide where we send in our laser. The light will travel around this ring feature here and come out here. And so we can channel light very easily, and we can actually channel it right through our mechanical devices. So here's our input. The mechanical vibration happens here. It is both a waveguide and a mechanical device at the same time. So when the light passes through that mechanical device, it imparts a signal onto the laser light that's traveling through that waveguide. And we can read out that signal, which is represented by this little black curve there. And so this is how we can actually track how fast these devices are vibrating. The reason we'd like to do that is because we want to use them as sensors. And so by tracking the frequency, we can actually track when particles land on these mechanical devices. So you can see in the picture here, this device is surrounded by particles, and when those particles land on the device, they stick. And that sticking causes jumps in the frequency. So this is frequency here, and this is time. So over time, the particles stick to that device and cause the frequency to change. And that frequency change can be directly tracked back to mass. So we can measure mass by observing this frequency change. Now, this is a very broad kind of technique, but there's a lot of applications we can use it for. One of them is to improve current scientific tools. So in science, we often have a sample. We don't really know what it's made up of. We'd like to know, take it apart, figure out what it's composed of. And the tools that we use to do that are often mass spectrometry or gas chromatography, just to give you 2 examples. These technologies are very important, but they're costly and they're big. So you can see this is a mass spectrometer. Compared to the size of this computer, it's quite large. So if we could shrink that down and decrease the cost by using our small mass sensors, that would be of great value to the scientific community. There's also potential for this type of technology to be used in security or defense applications. So this works a little bit differently. We'd actually coat our devices with this receptor coating, which is basically a layer that's very sensitive to any types of explosives. And so what happens is when those explosives stick to that receptor coating, we get our frequency shift. And that frequency shift says, yes, there's this chemical here. They can detect that for the security applications. So that's how that would work. The application that I'm most excited about is actually for biosensors. So if we can somehow harness the power of these very small, very fast sensors to help in healthcare, diagnosing diseases for biological applications, that would be really, really amazing. And so the way that we could do this is by looking at 2 factors, sensitivity here, or analysis time here. Ideally, you'd like both to be as small as possible, so you want to be working there. The present state of the art is here. So what we'd like to be able to do is break through that dotted line and really try and make these devices faster, more portable, so we could access remote regions, that kind of thing, just to try and really improve this technology. Current mechanical sensors are sitting here at this green line and the blue line there. But our devices are very sensitive because of our light technique that we use to look at the mechanical vibrations. So we're hoping we can really take these sensors to the next level. So what specifically are the challenges, and what am I working on in particular? So there's two main challenges as I see it. There's robustness and there's versatility. So for robustness, we have light, we have mechanics, we have lots of complex interactions at the nanoscale. They need to make sure that these interactions are working together how we want them to be, even when we put them in all these different environments. So it's a design problem in terms of designing these to work together in a way that is consistent and works in lots of different environments. The second problem is versatility. So these devices to date have actually had a little bit of trouble working in different environments, in liquids at high pressures, things like that. So what we'd like to be able to do is redesign some of these devices, make them smaller, look at different devices, try and get these able to be used in liquid environments and high pressure environments so that we can really take full advantage of the sensitivity of these kind of devices. So in summary, I've shown you how light and mechanics can interact at the nanoscale as highly sensitive mass sensors for a wide variety of applications. I've also shown you that versatility and robustness are two important parameters that I'm exploring in my research right now. I'd of course like to thank everybody who's helped me along the way, including my lab and my supervisor, Dr. Wayne Hebert, and the Faculty of Engineering for inviting me here this evening. Thank you.
Okay, Nir, can you top that? I'm sure he can match it.
All right, good evening, everyone. So I'll be talking today about femtosecond laser manipulation of single cells and neurons. So don't panic, I'm going to explain it all. So thank you for being here. Welcome, everyone, and enjoy the presentation. So what is femtosecond? Femtosecond is really, 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 really fast. It's a 1/millionth of 1/billionth of 1 second. So how many digits is this? It's 10 to the minus 15 seconds. So how fast is it? So really, we can't comprehend this such short time. But we can talk about how much light travels during this time. So in 1 second, light will travel 186,000 miles, which is about 3/4 of the way to the moon. But in 1 femtosecond, light will travel about 1,000 silicon atoms. During this time, the electrons in those atoms won't even have time to move. We call it God's perfect timing. So, okay, so now we said this is femtosecond, but how can we use it for something useful? So there's a famous relationship between a peak power of a pulse or anything to its pulse duration, which is inversely related, and the pulse energy. So just let's give an example here. So if we use a power, if we give something an energy of 1 microjoule, which is a really small amount of energy, and we deliver it during 10 femtoseconds, so we really achieve about 100 million watts of power. So I'm going to try to simplify it a little bit. What this tells us is that we can focus energy in time. So we can focus energy in space, and I'll demonstrate it here. So if I'm going to take a sheet metal and I'm going to hit it with a hammer, you see I'm bending it, I'm twisting it, and I'm not really puncturing a hole through. But if I'm taking the same amount of energy and I'm going to puncture it, in a really tiny, focus it into a small space, then I'm going to get a really neat hole in there, and I'm not really going to affect the entire sheet metal. So this means that we can focus energy in space, and the same way I can take a laser beam and I can focus it using a lens into a small spot. Now time, femtosecond. So I can also focus energy in time. And to show this example, so if I'm taking, this is my hands, by the way, doing it at home. So if I'm taking a screwdriver and trying to slowly push it, you see how it bends and twists, and eventually I'm going to make a hole there. Here's the hole. And then if I'm going to just do the same thing, but I'm going to do it fast, I'm not going to bend the sheet metal as much, and I'm going to make a really nice tiny hole in there. So now imagine me doing this in a femtosecond. Can't really do this, but... All right, so then we say, okay, so what we've done in our lab, we use this technology to perform something called nanosurgery. Surgeons use tools like scalpels and stitches in the surgery room, but what we wanted to do in our lab is we said we wanted to take it to a more basic level and perform surgery on a single cell to study what happens to the cell, to see what can we gain from this. In order to do this, we have to use laser, and we have to deliver kilowatts of power to the cell in order to perform this surgery. But we can't, if we do this with any regular laser beam, then we'll just destroy the cell. So if you think back about what I was talking about, focusing energy in space, but also focusing it in time, that tells us that we can do this very, very precisely. So that's why femtosecond laser is ideal, because we can deliver energy without inducing heat and without inducing mechanical shock wave in the cell. So let's move on and talk a little bit about some things we've done in the past in our lab. So we took a single cell, this is a kidney cell, and we cut it into small pieces using this technology. So this is where, oh, I have a laser beam. So we can, this is where the laser spot is, and we can just cut it into smaller pieces. So this is when we've gone up and down, and then even smaller. So then we said, okay, let's do something a little bit more useful with this, and let's try to do a nanosurgery on a live embryo. So this is a zebrafish embryo, and each embryo it's composed of a chorion, which is this I forget that I have a laser. It's a jello-like structure shell, which is right around here, and then it has the yolk and the developing cells. So this is a video of us performing the surgery, and you see this is exactly the same picture. And so we're focusing here. This is one of the cells. This is the second cell. This is the third one. You can see the membrane, the outside membrane. And then we focus, and you can see right here, this is the laser pulse shooting at this cell. And what happens is the surrounding material, it actually makes a little pore in the cell, and all the surrounding material just rushes into the cell, and then the cell automatically just closes up. And really nothing, it doesn't affect the cell. You can see here that the cell just keeps behaving as normal. So then here are some of the results of this experiment, and what we see here is that we can do something called transfection, that's introducing material into the cell. So we put fluorescent dye in this chorion, and then we shoot those laser beams right here in those two cells, and then you can see how they glow. That's because the fluorescent dye rushed into the cell and stained it. So then we said, okay, we can put material in here, but maybe let's do something a little bit more useful. So what we decided to do is we decided to try to do something called gene therapy, which is deliver genes into the cell. So we delivered genes that express in the fish bones, and when they express, they produce a protein that fluoresces. And so you can see how in the bones, how this protein accumulates, and then they fluoresce at this point. We also looked at those cells developing for a few days after, and we see that they keep developing normally and everything functions properly. So that tells us that our experiment was working. We delivered a gene to express in a certain location, and it did. And also the embryo kept developing into a normal fish, and it did. Okay, so until 2014, people used femtosecond laser technology to ablate cells, which is kit and destroy them, cut them, transfect them. However, in 2014, we came up with this paper with a new technology in order to use this tool towards attachment of cells together, kind of making a surgery. So here I'm going to demonstrate, this is a video of me attaching single cells together. And so, oops. So this is a retinoblastoma cell which was dyed with a fluorescent dye, and this is the laser beam pointing at it. The reason it's green is because this one has a fluorescent dye in it. However, the surrounding cells that will be in this video does not have a dye. And so I'm moving the cell around, and then you can see here those laser pulses, and then you can see the attachment happen just right now. There's going to be another one right here. So that was the second attachment, and then I'm going to take this group of cells and attach them right here at the bottom to another group of cell. And you can see they're attached right now. So what we did with this is we also looked at it under fluorescence microscopy as well, and as I said, the center cell was dyed, and the surrounding ones weren't dyed. And if you see it's hard to see here, I guess, but if you can see, only the center cell has the dye inside, and the surrounding cells doesn't have any dye. And that tells us that during this procedure, we didn't really interrupt those membranes, and we just attached those membranes to each other. So what we really did is, we call it molecular surgery. Each cell membrane has 2 layers of phospholipid molecules, and when we bring them together, and we shoot the laser pulses in this region here, what we're doing is we're removing those molecules that are on the outer membrane of each membrane, and here we're talking about 10 nanometers each membrane. So we're removing those molecules, and then we're left with those free molecules right here and here. And these seek each other, and eventually when they find each other, which happens really fast, then they just form a single membrane that's joined to both cells. So then we said, okay, let's take this to something a little bit more useful, and then we said, how about we'll try to connect neurons to each other? So our nervous system is comprised of nerves, and these nerves are comprised of neurons. Each neuron has a cell body, which is called soma, which is this part right here, and they have axons, which is those hair-like structures that transmit the signal. So then we brought one axon of a neuron into another cell body close to it, and then we delivered the laser pulses in order to perform the attachment. So you can see this procedure done in this video. So this is the neuron that we're focusing on. And then you can see how I'm moving this neuron, and one of its hair-like structures is touching this another neuron at the bottom. And I had to skip it because otherwise it will take too long. And you see the attachment right here just happen. And then I'm going to skip some steps, and then I'll bring both cells to another neuron and touch it with this hair from this original one, and then perform the attachment right here. And once the attachment happened, then you can see how I'm moving all these 3 cells as a single group, just to show that they're all attached together. So really, this is the first time someone ever done something like this to attach single neurons together. So lastly, the last thing I want to talk about just in general, so some of the applications of these technologies, so these technologies can be used to further research in cell biology using cell nanosurgery or embryo surgery or cell isolation. We can use it to further research in cell communication. And the attachment can be used to create artificial tissue. I created different structures just the way I wanted them. You can use it to study neuron degeneration and conduction block and nerve attachment. So thank you for giving me 600 quadrillion femtoseconds of your time. Thank you.
Thanks very much for a great presentation. And so next we have Catherine, who will tell us about her work.
Okay, so thank you again, everyone, for being here tonight. Tonight I'm going to talk to you a little bit about some of the work that I've done as a small subset of the BLINK group. So this is the Bionic Limbs for Improved Natural Control group. It's a huge interdisciplinary team that we've got going on here at the University of Alberta. So I'm just going to talk about my research specifically and how that fits in, but there's tons of other stuff going on that's really, really exciting as well. So as an introduction to this topic, many of you have probably heard of prosthetic limbs. These are typically prescribed to amputees, so people who are missing parts of their arm, parts of their leg. And the typical and traditional prosthesis is actually body powered, so it hasn't changed much since World War II, those ones with the hooks on the end. And they're operated with cables. They're fairly simple. More recently, though, there have been developments in robotic, or these myoelectric arms, which you can see here in this picture. So these are really, really exciting arms. They operate by recording muscle signals and using those to close and open the hand and change between joints. But one of the big, huge drawbacks right now is that a lot of these hands actually lack a form of sensory feedback. And definitely they lack an intuitive form of sensory feedback. So to give you an idea of what this means, imagine trying to pick up an egg and you don't know how tight you're squeezing it. You have no idea if you're squeezing too hard or too softly. There's not much visual feedback. It's not going to change shape or change geometry. So you're basically staring at that egg very, very carefully to try and get an idea of what's going to happen to it. And you can imagine that without knowing how tight you're squeezing it, it'll very easily crush. So we're trying to focus in on this problem and help to reduce this to overall improve the quality of life for different amputees. So first I'm going to talk about a very interesting and novel surgery that's happening. This was invented by a doctor in the Rehabilitation Institute of Chicago, Todd Kuiken, and we're using it here in Edmonton. We're the only center in Canada that actually performs this surgery. And essentially what the surgeons are doing is they're taking the nerves that used to go to the hand, which are now not connected to anything, and they're moving them to new places to sort of reprogram the body. So we're taking the motor nerves that used to tell the hand to close, and we're putting those into muscles such as the bicep and the tricep. So now when that amputee thinks, I'm going to, say, close my hand, now their bicep will start twitching. We can put an electrode on there, record that movement, and use that to close the hand. So it's very intuitive. They just think about closing it, and their hand closes. And what the surgeons didn't necessarily expect was that over time, not only do these motor nerves grow into the muscle, but the sensory nerves actually grow into the skin areas. So what this means is now if I touch that area that's been reinnervated, it feels as though the amputee is being touched on their hand or on their missing hand. So what we can do is we can harness the surgical technique, and we can use that to enhance our sensory feedback. So my work is focusing in on developing a device which will actually provide a pushing force onto those skin sites and give us that sensory feedback. So there's tons of different research that has gone into this in the literature. There's all kinds of different ways to provide this feedback, from pushing forces to vibration to electrical signals. We're focusing in particular on pushing forces, or mechano-tactile feedback. So what you can see here in this image is a simplified kind of schematic of what we're designing. It's called a tactor. And essentially what you'd have is you'd instrument the prosthetic hand with little sensors. They'd record the force that that hand is feeling, and then that would be translated to a pushing force onto that skin site using this tactor. So while there's been a lot of research into investigating different types of tactors, seeing how they work, one of the big problems right now is that they're actually quite large. So they take up a lot of space on the arm. They use up a lot of power. And you can imagine if you're trying to walk around a corner or put your arms down, they might get in the way. So the other issue to consider here is that this part of the arm, the residual limb, has a lot of really important stuff going on top of it. So not only do we have multiple tactors, like I'm talking about, we've got multiple sensors, which are measuring those muscle contractions. We've also got to have the socket itself, which is actually attaching the prosthetic arm to the limb. So there's a whole bunch of stuff happening in a very, very small area. And what we're trying to do is look at how we can save some of this space. So the idea that we had was to create something we call a cable-driven tactor. So why don't we take the part that's really bulky, the motor, and put that somewhere less important, say on the shoulder or on the forearm of the prosthesis. We can use a special cable to connect that to the tactor head, or the part actually touching the skin. And in that way, we could actually save a lot of that really, really important space on the arm right here. And so that's exactly what we did. Right here, you can see a 3D rendered image of our model. So this is the cable-driven tactor, and I had a video, but I'm just going to talk you through because it wasn't working. So essentially, we've got a little motor here, which is going to rotate that pinion gear. As that rotates, it's going to translate a force to a linear force along here, and that's going to be pushing on this specialized cable. The cable is going to travel through a conduit to wherever we need it to go, and that's going to push this tactor head in and out of the skin, proportional to whatever we're telling it to do. So whatever it's recording on that hand, it'll push into the skin, proportional to that measurement. So Kent Herrick was a summer student that worked on this project before I got onto it, and he actually created the very first prototype of this design. And essentially what he did is he took a flexible piece of plastic, attached it to his arm, and then implemented one of these tactors on top. And so what he was able to do is he could actually measure a force, and he could push into his arm. So he was just trying this out on himself. It was really, really exciting and really promising work. So when I started my master's, we developed a tactor cuff. So we wanted to make it a little bit more realistic of the real situation of what amputees are seeing. So we used rigid materials, just like a socket. We used 3 tactors because we want to provide more information. And I can go into a bit more detail later if anyone's interested. But we actually used a really, really cool new manufacturing method that you may have heard of called rapid prototyping, or 3D printing. So if you haven't heard of it, essentially if you imagine just taking like a glue gun, you're basically heating up plastic and laying it down layer by layer, building up these layers until you have your 3D part at the end. And it's really exciting to work with this technology because it's incredibly inexpensive and it works really, really quickly. So this tactor cuff here, to have that machined, patient-specific, would be hours and hours of machinist time. It would be very, very expensive. But using this 3D printing technology, we printed it in under 11 hours and for less than $8. So it's really, really inexpensive and awesome way that we can move forward get these prototypes designed, built, and tested in a really rapid manner. So we've started looking into testing of these systems, trying to optimize different parameters. The first couple things we're looking at are minimizing the overall weight and cost. So one of the reasons that many amputees will actually reject the use of their prosthetic arm is because it's too heavy or it's not very comfortable. So if they're spending, say, upwards of $100,000 on a prosthetic arm, and then it's too heavy, so they leave it in their closet, we don't want that to happen. So if we can make this really, really light, hopefully that'll help with clinical implementation. Additionally, we want to keep that cost as low as we can. Again, we don't want to be going above and beyond what people are willing to pay for these items. So keeping that low is also something we want to look at. We actually had a summer student in this summer who's working with me, and she was looking at the friction in the system. So she was looking at ways that we could bend the cable, stretch, look at different lengths, and how this would affect the amount of friction that's in the system. And this would have an impact on the size of motor we'd have to choose. So if there's too much friction, we need a larger motor, costs more money, it's larger. So how can we actually improve those situations? And more recently, we also looked at optimizing the tactor heads, the parts that are actually touching the skin. So is there any way that we can choose particular shapes and sizes that'll actually give us better information and more comfortable manner? And this way we could kind of make a standard optimized recommendation for these tactor heads across studies. So in the future, we've got tons of areas to expand into. I've got about another year of my master's, so I'm hoping to get this clinically tested on a few of our wonderful volunteers. Before we get to that, we're going to be implementing a new control system. So right now, we can tell it where to go in space, but we want to be able to tell it how hard to push onto the arm. So we need to implement a control system for that. And we also want to get this onto a socket. So I didn't mention, but the way sockets attach to the arm is typically a vacuum seal. So you open up the bottom, you put your arm into it, and then you seal it off, and now it's sort of suctioned onto your arm. But you can imagine if we're now poking holes in it to be able to push on their skin, you're going to completely obliterate that suction seal. So we need to figure out a way to work around this and get past this problem. Once we've got that figured out, we're going to move into validating the function. So how does this actually affect the pressures that are on the arm? Is it making it more uncomfortable? Or maybe is it starting to fall off their limb? And finally, how is their visual attention changing? So do they still have to stare at that egg when they pick it up and move it? Or can they now rely on their sensory feedback and be more confident with what they're doing and pick it up and look where they're going and put it down just as someone would in a day-to-day activity with a normal limb? So with that, I'd like to thank you very, very much for your attention, and I'd be happy to answer any questions that you might have.